Okay, very good. We are going to resume the program, and the next speaker is Kristan Jensen from Victoria, and his title is Norm of the No Boundary State. Yeah, please.
All right. Can you hear me? Is the microphone on? Okay. Thank you so very much to the organizers for putting together this lovely meeting. It's wonderful to be back in Seoul and to see all of you. So this talk today is a talk about de Sitter quantum gravity. What I have in the back of my mind the entire time is Einstein-Hilbert with positive cosmological constant. And everything I'm going to do today, despite the title of this workshop, is not going to involve string theory per se. I'm going to work with effective field theory. So I'm not going to ask how on earth I get handed this. I'm not going to ask where it comes from. I'm not going to ask or deal with any vexing questions, eternal inflation this, or the construction of de Sitter vacua and string theory that. Those are all wonderful and important things that are above my pay grade. My goal today is simply to study some aspects of de Sitter gravity within the effective field theory approximation, following the rules of effective field theory. And so what's my approach for the talk today? I need to develop some background first to discuss the main questions of the talk, the no boundary state, and the behavior of its norm at very late Lorentzian time. Need to build up some ingredients to even approach that question. I'll talk about some late time features of the wave function of the no boundary state, and then I'll talk about the norm itself. And I also have another compliment to the organizers. The putting Shota and Tarek and me on the same day has been very nice. I think some of the ingredients are flowing nicely from one talk to the next. And certainly Tarek has already identified many of the issues that will come up in the talk today. Right, so when we talk about de Sitter gravity, the very first thing that we should think about are the classical solutions to that model. And the basic one is the one that Tarek mentioned earlier today in his talk, namely global de Sitter space. And the line element for that space I can take to be minus tt squared plus cos squared t, and then a sphere. And the Penrose diagram for this space looks like this famous square with time going up and where lines of constant t are spheres. So the sort of picture that we have for a space-time like this is one where you prepare a sphere in the far past. It's really big. As time goes on, it gets smaller. And then eventually hits a bottleneck where it has a minimum size, the cosmological scale. And then it goes back up again, blows up into the far future. Here's past infinity. Here's future infinity. And I'm going to work, I guess, with something like this. I'm going to work in units where my ADS, my de Sitter scale is just 1. I have unit radius. And global de Sitter has all sorts of interesting physics in it. There's various patches that you've heard about at various times in your life. There's an inflating patch, which is like the upper triangle here, where usually you would write things down in terms of constant time slices that are flat space. There's also a static patch, or rather infinitely many static patches that look like that, where I can use different colors. Look like the interior of that diamond. De Sitter, of course, does not have a time translation symmetry, but in the inside of a static patch, there is a time-like killing vector. And you can pick coordinates so that in here, we write out the line element in such a way as to manifest that time translation symmetry. You can write it as r² - 1 d tau squared, the r squared over r squared minus 1, r squared d omega d minus 2 squared. And you stare at that for a moment, you notice that that's static patch is bounded by a horizon. It's exactly this point right here. There's the so-called cosmological horizon right here at r equals 1. And if you follow your nose, you might be tempted to associate to that horizon an entropy following Bekenstein. Would be the area of that point. Well, that's that surface rather. So the volume of this d minus 2 sphere in units of 4g Newton. And in de Sitter quantum gravity, I think it's safe to say, if you disagree violently at this stage, please let it be known and let's talk about it. But is this entropy meaningful and what does it mean? That is a very basic question of de Sitter quantum gravity that remains unaddressed. Does it count states, for instance? The answer is unknown. And this should be particularly vexing for us, not just from an abstract theoretical point of view, but even a practical one. I think it's safe to say that over the last few decades now, the principle that black hole entropy is a very important thing to follow has been a guiding principle in our research in ADS CFT and quantum gravity more generally. It's been extraordinarily fruitful. It's suggested many questions for investigation. And what are the right questions even in de Sitter? Well, it's still a matter of much debate. I think including this one right here. So, of course, that's not to say that hasn't been various proposals for what the horizon entropy means. There's various ones. So one proposal, for instance, there's not just one proposal, there's many. One is that when we talk about de Sitter space, that we can think of the static patch of de Sitter as a quantum mechanical system with a finite but non-perturbatively large dimensional Hilbert space. Some evidence for this comes from the fact that the horizon entropy, or the horizon area, obeys a gravitational first law and it has a minus sign in it. If you stick a black hole in the center of the static patch, raise the energy in the static patch, the entropy, total entropy, the one coming from the black hole entropy and the horizon entropy, decreases in a way that is reminiscent of the behavior of a finite dimensional Hilbert space at the entropy maximizing point in the spectrum. So that's one possibility. There's been other various proposals. You might think of it as entanglement measure between complementary static patches. Another one is, maybe it's a measure of how many initial conditions you can prepare in the far past that blow up, that evolve in such a way that you remain non-singular and evolve into de Sitter in the far future. But we really don't know. One, sort of in the vein of the first proposal, the idea that you're counting dimension of some Hilbert space, well, it may be, let's see, it's a way of saying this. So you might be tempted to think about the approximation of quantum field theory in the static patch, neglecting gravity. And for QFT in the static patch, Well, if you bear something you might be tempted to do, take the line element in the static patch and analytically continue to imaginary time and change variables. Just let r equal sine theta. R here goes between 0 and 1, so that's a perfectly valid change of coordinate. And you get a very familiar space. You get cos squared theta d tau Euclidean squared plus d theta squared sine squared theta d omega minus 2 squared, which is just a d sphere written in some d minus 2 sphere slicing. Locally, it's that under the proviso, and globally, it's that under the proviso that you identify tau e with some 2 pi periodicity. And from that, you would say, well, there's a natural state then in the static patch, the thermal state with respect to that time. And de Sitter looks like the thermal state then at inverse temperature 2 pi. Or that is to say, you would write the sphere partition function for field theory as trace e to the minus 2 pi k, where k is the generator of tau translations, and the trace is taken over states in the static patch to the extent that that makes sense. You know, we've become a little bit more sophisticated recently and learned that that doesn't really make sense, that if we take local field theory and we restrict to a subregion, then we don't really have normalizable density matrices on there and so on, but okay. So we conclude this. And you might wonder to what extent there's similar relations that hold once we turn on gravity. How much still holds?
How match with the other philosophy that there should be just exactly one state?
So here we're talking about the static patch and not the more recent thing that's been on people's minds about globally there being one state. So, and how do those things match is another great question.
Yes, another thing that sort of
that if you take one global state and trace out a region, then you would end up with a very large. Yeah.
If I just take the global thing, take T to I T plus I upon T and something like that, that also becomes a sphere.
I'll explain the relation with a sphere shortly. Yeah. You'll see that soon. I mean, that has to do with a particular state in de Sitter, the no boundary state. So I guess I forgot to say the most important part, which is that in a building on these ideas, Gibbons and Hawking long ago argued that the cosmological horizon entropy is related to the sphere partition function of gravity, at least in the loop expansion, using similar ideas as this. And what they said was that C sphere should be equal to E to the S Cosmo. And well, that's an interesting proposal. We can make sense of the sphere in Euclidean gravity, and we can even have some prayer of going beyond the tree level approximation and asking about, if that's really true, about the horizon entropy at loop level. And then there's some problems that come if you take this idea seriously. One is that, well, if we talk about a static patch, then we have to confront the question of which static patch. Since there's infinitely many of them. We also have to confront the fact that, famously, the sphere partition function in gravity, unlike the sphere partition function of unitary quantum field theory, is not necessarily positive definite. In fact, it has a phase, an alternating phase that's become very popular lately that Polchinski found in 1989. It goes like I to the d plus 2. Incidentally, if you want to know where that phase comes from, it's very easy to discuss. Just come and find me afterward. The other thing that I think is a problem with this is that the idea of an isolated static patch, like static patch is an isolated quantum system in de Sitter, it seems conceptually wrong. For the following reason. So if we go back to our Penrose diagram for de Sitter up here, what we really have when we talk about a static patch, we have a static patch and its complement over here. But now imagine perturbing the initial conditions slightly. Send in some matter in the far past, and it back reacts. And unlike the situation that we are familiar with in ADS and two-sided black hole, where you send some matter in and the Penrose diagram gets squashed, increasing the separation between two boundaries, here it gets flipped. The Penrose diagram gets lengthened. And now, well, these two patches would they would come into causal contact with each other. So shock waves in the far past, perturbations in the initial conditions in the initial state will bring the static patch in contact with the outside world. So this is all to say, it's very there's many questions and many problems that are ripe for investigation. Another way of thinking about these issues that's kind of related, it was the angle that we took for our project, well, is to think about the sphere in a slightly different way. So here's our friend, the D sphere. And the way to think about this picture here is that in the sphere, imagine taking North Pole and the South Pole. There's a surface that we get of codimension 2, or sorry, codimension 1, but going down like this. That is the static, that's the Cauchy slice of the static patch. And where this variable here, this is tau e. So you bring it around by 2 pi, glue it back to itself. That's the sphere. That's the picture for this. That gives one interpretation of the sphere in terms of the Hilbert space along that interval. But there's another picture that we can slice this and dice this another way. We can slice it along the equator. And think of the sphere as taking the state that is prepared by a hemisphere and computing the inner product between that state and itself. The state that you get that's prepared by Euclidean path integral on the hemisphere is called Bunch-Davies. You can think of computing the wave function by fixing data like quantum field theory degrees of freedom on the equator and then evaluating path integral over conditions that respect that boundary condition and where you're smooth everywhere in the interior. And this gives you a state. You can call it BD as a ket, BD as a bra. Actually, I'm going to give them tildes, my own personal reasons. And for quantum field theory, at least, the overlap of those two states is nothing more than the sphere, right? If I take the wave function, fix phi here, wave function, fix phi here, multiply them together, and then integrate over phi with the right measure, I've just cut open and then re-glued the sphere path integral. Haven't done anything. Well, I can take this state and I can evolve it in Lorentzian time and see what I find. Yeah, of course.
I think that UFT, maybe this is appropriate sphere partition function.
Yes.
But in gravity, I think it's less clear. There's some discussions by Weinberg about how this diverges usually. The total counting on the side of producing gravity. Maybe it's not quite normalizable state.
Sphere theory because of the performance mode.
More about the question of fixing the time. Usually when we have a little bit of space, we have to fix the time, but in gravity, there's different morphisms in there. So we have to somehow gauge fix in an appropriate way. And then when we misperceive in gravity, not really selected properly.
So I have some words on this piece of paper that are some version of what you just said. Indeed. So where we're going with this, indeed, this is field theory, but we want to say something about gravity. There's a similar state that is prepared by Euclidean path integral in gravity called no boundary or Hartle-Hawking state. And I would like to ask a similar question, whether there's some relation between the norm of that state and sphere path integral. However, I'm not smart enough to be able to know what's the right recipe for computing using the Euclidean path integral the norm of that state. So how can I do this? That's where this talk is going, but how can I do it? Thank you. So one idea, well, even in the quantum field, for quantum field theory in curved space, if I take this state, this, what I'm calling BD tilde, at, say I consider the state on the boundary of the hemisphere, well, I can evolve that into Lorentzian time, where the sphere analytically continues to de Sitter. And then I can evolve the state forward, and I can get a new state at very late time I'm going to call BD, which of course is related unitarily to the state here at t equals 0. So I can equivalently think about the state at late Lorentzian time. Incidentally, the sort of picture for this, what we're dealing with, in terms of the de Sitter line element that I wrote earlier, I have a Euclidean cap and a Lorentzian segment that implements time evolution. That's a complex time contour that connects, in the coordinates that I used, the point I by 2 down. That's this. And then with a Lorentzian segment, that's this. And now the big question is, what happens in gravity? There's a similar recipe for constructing a state in gravity. It's the same one that Tarek was talking about in his talk, the Hartle-Hawking state at late time. That's essentially, sum over metrics that fill in the boundary data smoothly. And semi-classically, you would get a geometry that looks like this, when the boundary is a sphere anyway. And, well, I'm going to call that resulting state at late time, instead of BD in gravity, I'm going to call it HH for Hartle-Hawking. I'm going to denote it with a double angle, because I'm talking about a state in gravity. And the thing that helps me here, I don't know what the right rules of the game are for computing inner products of states in gravity. especially when I'm summing over closed manifolds. But if I go to late time, well, space-time becomes very large. We have a good understanding of the possible boundary conditions that we can impose. And that corresponds to the Hilbert space of states at late time, and on which we can try to understand what are the rules of the game for computing overlaps. What's the resolution of the identity and so on. So the strategy in this talk, I want the norm of this state out here in the far future. I want to understand what this thing is in terms of perturbative gravity at late times. I want a real recipe to discuss this, and I want to ask the question, well, what on earth is going on between this and the sphere path integral? What's the relation between this and z sphere? If I consider a norm of a state, I would expect that to be real and non-negative. What on earth does that have to do with Polchinski's phase and so on? And the approach that we took in our manuscript was largely exploratory. We have all these sort of different objects swimming around. How much can we compute and really relate to each other? So the sort of questions that we had on our mind, I can write 3 of them down here. Yeah, it's completely, well, depends on your choice of gauge. If you work in the natural one that decouples the conformal mode, yes, it's because the conformal mode, if you've ever seen that.
The wrong sign. I mean,
well, yeah, it's only mostly wrong sign. If you've ever seen The Princess Bride, then it's only mostly dead. What happens is there's the L equals 0 and the L equals 1 modes of the conformal mode are actually right sign. So when you rotate the whole mode to get rid of the rest, that's fine. That incurs no phase. There's no Jacobian. But then you have to rotate back L equals 0 and L equals 1. L equals 0 gives you 1i, and the vector gives you d plus 1 more. Okay. So some questions that were on our mind. One was, what's the relation, if any, between the sphere path integral and this norm at late time? Sort of what's the physics of Polchinski's phase in Lorentzian signature, if any? And the third is, what on earth, this I to the d plus 2 is very troubling from the point of view of asking this question about static patch entropy, right? If the sphere is e to the static patch entropy, quantum mechanically, the sphere has a phase, then the entropy is not positive definite. You would get a pseudo entropy maybe along the lines of Tadashi's talk yesterday. Is that the right way of thinking about it? Is there something else entirely? Is there a better measure that's automatically positive definite? Many questions, few answers. So what can we say? What's the fate of the static patch entropy? And already I've blasted through half my time. So maybe I'll say what some of our main results were, and then try to explain where these results came from. So some results. So the first, our main result is that was extremely surprising. It was not what we expected. It was that if we compute the contribution to this norm, where a future infinity is a sphere, nothing else, there's no like torus or something else or multiple universe contributions, we just consider the one sphere. we expect that at future infinity, we should sum over everything. So this is just one part of the answer, but it's the part that's the biggest by far. What you get is e to the s naught times some positive constant upon renormalization, some ratio of one loop determinants of non-zero modes. There is, so e to the s naught here is the tree level horizon entropy. So volume of SD minus 2 by 4g Newton. There's a logarithmic correction, S naught, that goes to the minus d plus 1 by 2. But then this is over something. It's over a volume factor of isometry. It's over the volume of SOD comma 1, the isometry of de Sitter space. If I contrast this with the sphere path integral of Einstein gravity, that goes like some constant that's positive, Polchinski's phase, e to the s naught. There's the same log correction to the entropy. There's a volume SOD plus 1 that comes from properly accounting for the isometry of the d sphere. So we get something that's real and non-negative, which is what you'd like for a norm, but it's 0, actually. Which leads to the surprising statement that at least in this approximation where we have a sphere at future infinity, the state's null. That was one result. Another one, so as Schumett was kind of saying, it's a little bit in vogue these days to think about observers and such. So we asked the question, what happens if we have an observer in the game, or more precisely, a pair of observers, as in the story of Chandrasekhar, Longo, Pennington, and Witten from 2022. So we consider the problem where our state has a complementary pair of observers coming from a single world line. Looks something like this. Or from that point of view, Penrose diagram, where you have the future half of de Sitter, you would have world lines here and here that are connected in Euclidean time. And in this case, if the observer has we use this sort of world line model that's been in vogue. You have a world line that carries a degree of freedom q on it that's time independent with an energy m plus q, with q positive. If q is continuous, or sorry, is non-compact, sorry, p is non-compact, that corresponds to a continuous density of states for this observer. It's actually the same thing that CLPW we're considering. And in this case, we can go from something very large times 0 to just something very large. Some other positive one loop constant, e to the s naught to the d plus 1 by 4, mass of the observer to some power over now volume of SO d minus 1, which is the residual, the spatial part of the residual symmetry preserved by the world line. posed some questions. This is giving us some answers while raising other questions. So one, the sphere amplitude is simply different. At a technical level, the rules of the game for the Lorentzian norm and the Euclidean path integral seem to be quite different from each other. You know, when you compute the sphere path integral, you're dividing by diffeomorphisms on the sphere. And that includes, you have to treat the isometries of the sphere. That's what leads to this 1 over volume of SOD plus 1. From the point of view of the Lorentzian norm, the sort of contour, complex time contour that we're considering has Euclidean sections and Lorentzian ones, with a very long excursion, the long road to freedom. You go to late Lorentzian time. If I ask what the Euclidean isometries of the sphere analytically continue to, in real time, they become complex diffeomorphisms. Conversely, so if I look at the things that are real at late time, where I turn around and I integrate over metrics when computing a norm, if I divide by diffeomorphisms that are real there, that's precisely the conformal group, SOD, 1. So one of the things that seems to be different about the sphere versus the late time norm is the instructions for how we divide by gauge symmetry. And in addition, of course, to what the physics of the phase. Another thing that we get from this, as far as the second question, I definitely don't have time to talk about why this is. If you're interested, I can talk afterward. But there's another object that we consider besides the norm of the Hartle-Hawking state, or the wave function of the Hartle-Hawking state, which is the what we call the global amplitude, where we fix data in the past and data in the future, and we work perturbatively around global de Sitter space. You can think of that as a very long time transition amplitude. This thing has an extra phase beyond what you would expect. Even when your data is trivial here and trivial up here, you would expect that there's a time reversal symmetry classically. Quantum mechanically, that amplitude picks up Bolchinski's phase due to essentially the same physics of the conformal mode. As for this third thing, what's the fate of the entropy? I would say it's completely unclear, at least to me. Maybe it's clear to smarter people. The thing that, it's unclear because is the sphere a good definition for the entropy? Well, it has the alternating phase. Even with what Juan does, and including an observer in his paper from last year, it doesn't quite do the job either. So that's very puzzling, very perplexing. Well, this norm gives us something positive definite at least, although why should the norm count states? I know of no argument why that should be the case. If I am almost by answer analysis asking the question, what's something positive definite that agrees with the entropy at tree level but differs quantum mechanically, finite, non-negative? Well, this thing does the job. But is that the right thing to consider? Again, it's completely unclear to me. So there's lots of room for other people to come and join the efforts in de Sitter. Yeah. Sorry, can you? Yeah. Yes. It's infinite. Yeah, for us, it's infinite. So I haven't said what's the computation that gives this. I'm about to, with the time that remains, I figured it was better to give the results first and then as I have time. The way you may recall the usual bosonic string has a sphere amplitude that vanishes if for finite for compact target. That reason there has to do with there's some non-compact conformal isometry, and in that particular computation, it's very similar to what is going on here. In fact, it's almost the same computation, which suggests to me that that we should not regularize this. This is real physics. Yeah. I should stress too that this question, this infinity, this is very. I'm a very cautious and conservative person by nature, but to me, it really it raises my concern about the status of computation of CMB fluctuations in theoretical cosmology. So the state that you use when you compute CMB fluctuations is exactly this state. And what this is saying here, if the state is, or at least the sphere contribution to it is null, that's saying that we don't have a probabilistic interpretation for CMB correlators. It's like saying, that's what I mean by a probabilistic interpretation. So so the norm we get is 0, but something we could do is try to insert vertex operators on top of it, like what one does in worldsheet string theory. And then you can get something non-zero, as you say. But then, a normalized correlation function would be that thing over the norm. I'm saying that doesn't exist, which means I have unnormalized correlations which don't admit a probabilistic interpretation.
I thought it should actually have a cosmological constant term, which is the reveal term. Actually get some finite answer.
In worldsheet string theory, if you consider the sphere path integral, but where your target is non-compact, then there can be divergences, like in Liouville theory, for instance, where you have a continuum of states. Then what can happen is that you can have a sphere path integral that's infinity over infinity, which can be finite in a regularized sense. I'm saying that does not happen here. Maybe I should explain a little bit of where these results are coming from.
Your framework, isn't that just pure C equal to 0, not critical string? I mean, just pure real?
No, it's not. I'll explain.
Okay.
Well, I'll do my best, but if not, let's talk some more afterward. Okay, so we have to explain a little bit of the framework that goes into this. So the first ingredient, we need to talk about the late time space of states that we construct in de Sitter, and then the wave function of the no boundary state in that basis of states, and then to talk about inner products. How do we compute a norm? So our thing is, at late time in de Sitter, we have, and we can already see it from the metrics that we wrote down earlier, the space gets very, very large. And in general, not just for the particular solutions we were discussing, you get a space-time that has a line element that can be put into this Pfefferman-Graham-like form. Minus dt squared, e to the 2t, some spatial metric on the constant time slice, plus, and then I'm taking the corrections to be order 1 and purely spatial. I can always choose a gauge so that that's the case. In which case, my boundary data, the thing that would be natural to fix in the path integral would be this metric gamma ij, as in ADS quantum gravity. This is the analog of the boundary metric. And the gravitational path integral with some initial conditions, say that space-time caps off smoothly, and a final condition, fixed gamma, that's computing a wave function. That's giving us a wave function of gamma it's just the GPI. And I interpret this as the wave function of the late time state in a basis of states labeled by the boundary data, the thing that we fix. This is just usually what you do with path integrals. Now, writing down a space of states in terms of a boundary metric, the space of boundary metrics, that's not a good basis. It's overcomplete. For reasons that are not too surprising for those that have studied ADS-CFT before. This gamma is only defined modulo diff times file. One way of saying this is that, suppose we consider the GPI where we perturb gamma slightly by an infinitesimal diffeomorphism on the boundary. Not just for psi, for any state actually, not just for the Hartle-Hawking state. Saying the amplitudes are diff invariant under parallel diffeomorphisms at late time. As for Weyl, well, depending on the dimension, you can pick up an anomalous, well, not a phase, but an anomalous exponent prefactor. Familiar from the bioanomalies and how they appear in ADS-CFT. So this comes from parallel diffeomorphisms, this from additive reparameterizations of time, plus some compensating time-dependent diff of the xi, just like the PBH transformations in ADS-CFT. Punchline for this is that this wave function, psi of gamma, behaves like a CFT partition function, irrespective of questions that arise with DS-CFT of whether or not it's actually a bona fide CFT partition function. It behaves like one under diff times Weyl. These identities are saying that this thing, if I replace gamma with a local rescaling of gamma, I get the same wave function back up to an anomaly, just like a CFT partition function. So, but there can be anomalies. So for instance, in d equals 3, which is a case very close to my heart, you get an anomaly. So it's the same one that Tadashi was talking about in his talk yesterday. It's just the usual anomaly of a 2D CFT, central charge. Central charge at tree level is 3I by 2G Newton. There's a one-loop correction of 13 that I found some years ago with Jordan Kotler and Alex Maloney. I'll show up nicely in a moment. In general, in odd D, you get an anomaly that looks like that of even dimensional, in one lower. And with anomaly coefficients that at tree level are pure imaginary. In any case, you get a Hilbert space of states parameterized, spanned by, if you will, gamma eigenstates that form after division by diff times Weil some Hilbert space. And on that Hilbert space, we can argue for a resolution of the identity, which looks like a sum with the division and gamma Kepras. And, well, in order for this to even make sense, we need some notion of anomaly cancellation. It's worthwhile. So the way that this seems to work, as far as we can tell, and I'll tell you how far we've been able to check this, in odd bulk dimension, where we have these anomalies, this guy transforms with some weight under Weil rescalings, but then the measure carries the opposite one such that the integral is well defined. So to be a little bit more explicit about this, in d equals 3, where we know the one loop correction and we know something about the measure, in d equals 3, this Kepra carries an effective central charge that's the central charge that we would infer from the wave function, plus the one that we would infer from the complex conjugate wave function. So C plus C star. Just the real part, twice the real part of the central charge. So we get 26. Which is, the measure, once we carefully divide by diff times Weil with the right ghosts, of course, carries opposite that. We get a perfectly well-defined integral. And in general odd dimension, at least at tree level, the same sort of argument, the anomaly coefficients that would characterize the state and the bra are complex conjugates of each other, and the fact that the anomalies are pure imaginary, well, those cancel, at least at tree level. Okay, I can't get into where we do this resolution of the identity. It's analogous. There's still things to understand about it, but we follow similar methods to what we did in our study of de Sitter JT gravity in some papers over the last few years. I can talk more about that after the talk if you want. There's an important feature that we need for the wave function of the no boundary state in our analysis. So if we actually look at this psi in the Hartle-Hawking state, it's peaked around gamma is the round metric on the sphere, which means in the probabilistic sense that would suggest to you that the round sphere is the most likely configuration of space at late time. And that's going to be important for us because when we consider the norm, it's going to be some integral over metrics at late time. How do you compute the norm of a state in quantum mechanics? Integral dx. We're going to have an integral over these metrics at late time with a saddle point approximation, where the saddle is the round sphere at late time. Yeah.
analogy we apply mechanics at the end of the issue? Usually when we have to go to x, x
Yeah,
needs to be both positive and
right.
negative.
So what do we actually find here? We look at a resolution of the identity for those states where gamma is close to the round sphere. That's the thing. Yeah. So we never explore large field excursions, which would hit the boundary of space of smooth metrics. Yeah, that's right. So in low dimensional examples, sometimes you can explore like all the way to the edge of that space. Here, yeah, okay. I should include some kind of squiggle. This is some kind of squiggle. This is for gamma close to gamma naught. And that's the part that we need to discuss the norm when talking about states that are peaked near the round sphere. Okay, so behavior of these kinds of states. So in d equals 3, so we have an S2 at late time. And as you all know, any metric on S2 is diff times vio equivalent to the round one. So we can just fix, in other words, gamma be the round one, in which case, for very different reasons than in the recent discussion of 1D Hilbert spaces, we would end up with a one-dimensional Hilbert space at late time, with a single state, gamma naught, and the wave function of the universe is a number. And when we actually, we can go ahead and compute that amplitude. You fix round metric here, and you sum over metrics that fill it in smoothly. There's the saddle point. You can look at the spectrum of fluctuations around it. And what we get is some non-zero one-loop determinant, e to the s naught by 2, where s naught is static patch entropy, classically. And this one-loop determinant is just over non-zero modes. There's nothing terribly bad about it. And in fact, we can do better than that. We can evaluate the one-loop determinant. Its logarithm is proportional. It's just a volume counter term, basically, with a particular coefficient that we can compute. And in fact, is just encoding the plus 13 shift in the central charge. In d equals 4, the behavior of this wave function is like an e to the s naught by 2. There's a positive coefficient over 4g Newton, integral d3x, I'll call it d3 omega prime. There's measure factors. If our parameterize our metric fluctuation as h, and we have like an h at omega, h at omega prime times or dotted into the tensor structure of a 2-point function of a stress tensor on a sphere, which is fixed by conformal invariance up to a number that we take to be 1 in this normalization. So you end up with something, what is this? This is a glorified Gaussian wave function in terms of all the metric fluctuations away from the round one. And it's non-local. In 5 dimensions, you end up with a wave function that's expressible locally. And it looks like the Weyl tensor squared to quadratic order in fluctuations. So you get some wave functions. These things are, at least the exponents are computable using classical gravity. It's difficult, but it's not terribly challenging. It's the tensor. You could think of it this way, assuming, well, with some. It's so the tensor structure TT is positive definite. It has to be, I'm not asserting that there's some CFT dual. This is the structure. It's convenient because the wave function respects conformal invariance, to write it in a basis of things that we're familiar with in CFT. Okay, so I'm basically over time. I won't, and it's the end of the day, and we all, at least I'm a little tired and jet lagged, so let me just wrap up extremely quickly here. The idea then, once we have we know something about the wave functions, we know something about a resolution of the identity, then we can compute a norm. Just by inserting 1 intelligently. Thing is peaked close to the round metric, and so the perturbations are quite damped. There's a nice saddle point approximation that emerges at small g Newton, and what you end up with, well, the wave function has that e to the s. Well, maybe I'll just say something. Let's see. So you get a saddle at gamma equals gamma naught. The point is, the wave function is just some, after renormalization, some number times, these distributions. When we integrate over metric fluctuations, then, how do we do it after dividing by diff times vial? Well, we fix a gauge that, just like we do on the bosonic world sheet computation, blah, 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 blah. Say you fix the trace of H to be 0, you fix H to be transverse. That exhausts the gauge freedom locally, but not globally. What's left are the conformal isometries. Fixing you get all the integral over the rest of the modes of H that are transverse traceless. That produces some glorified Gaussian integral, which is non-negative after renormalization. But there are these residual gauge symmetries of the path integral, conformal isometries. And that's how, from the point of view of actually fixing the gauge, using Fadeev-Popov, et cetera, that shows up in the form of some ghost zero modes, just like for the sphere amplitude of bosonic string theory. And that's what leads to this factor of 1 over the volume of SO d comma 1. In 3 dimensions, we can be very, very explicit about this. Let me just write the formula real quick. And so in 3 dimensions, we only have a 1D Hilbert space at future infinity. So this norm, again, just the one sphere, is the wave function complex squared over the inner product of this one state with itself. And when we look at that inner product, it's some, it is itself some gravitational path integral over metrics that interpolate between the sphere and itself at late time. And that amplitude, there's a whole ton of non-zero modes, but there are zero modes that act as relative conformal transformations that are twists between the 2 boundaries. So this thing right here is proportional to volume of SO 3 comma 1 due to those bosonic zero modes, and that gives us a complementary perspective. It's the same result as we obtain from an integral over metrics mod diff times vial. I've gone over time. I apologize. There are many other directions that we're exploring. There's many other things to be done. Certainly more than I have the time to do. So if and there's just many basic open questions. I think this is a point that was emphasized nicely in Tarek's talk as well. More people are needed to do this. And on that, I will end and say thank you very much for your attention.
Okay, so yeah.
So is this your norm here for the whole concept? So since you're only considering single large universes in the flight region, does this coincide with our Wheeler DeWitt norm?
Good. So, good. My understanding of this at the level of parroting other people is yes. There's a recent paper. Well, okay, so there's, this is being recorded too, so it's very embarrassing that I'm saying this at the end. So there's a lot of harmony between the things that I'm saying, sorry, Subrat, and a couple papers of Subrat Raju from 2023, where they analyze solutions to Wheeler DeWitt at late time, and they, on very general grounds, find solutions to be constrained in ways that, the same ways that we find just by directly solving Einstein gravity. And then they discuss also the construction of unnormalized correlation functions in their work. And right, so this, they don't in their papers argue for, they say that this kind of norm or inner product and integral over conformal data is very natural. And then they show, once they insert enough vertex operators, that it's related to Higuchi's fold group averaging norm in the G Newton to 0 limit. That's sort of resonant, but that's not. Yeah. Well,
then somehow, like in the single universe, single universe, something like this.
yeah, the paper that that says that I think it's, but maybe I maybe have learned the wrong lesson from the paper. I'm still studying it. It's a paper from Henry Maxfield and Jesse Held that just appeared like a week and a half ago or so. What I did, I had a little bit of email exchange with them. What they are doing is equivalent to this, but I guess you're raising the question of whether that's equivalent to Wheeler DeWitt norm. Okay, okay. That could very well be. It's something that I am still learning about. So.
This was probably asked and answered to conformal model. So you're saying conformal model can give you exactly how, is it basic fixing procedure that removes the. So
this is not the conformal mode in the bulk. So when we consider these inner products, we're writing this as some integral over the late time data. Hey, what? There's a wave function. There's its conjugate. And what we're integrating over in the norm is the data at the turnaround point at late Lorentzian time. And yeah. So to get the wave functions to one loop, you have to deal with the physics of the usual conformal mode. That does not lead to any problems in this context. Or rather, it doesn't lead to any more than the usual problems. Like it's all wrong sign, but it's unlike in the computation of the sphere amplitude. There's not this presence of some modes that are right sign and everything else is wrong sign. The whole conformal mode is wrong sign. So when I say it's fine, I mean you rotate the whole conformal mode. Yeah. So that the conformal mode confronts you in this computation. It also confronts you in the normalization of the measure at the turnaround point, but not in any terribly bad way there. The thing I was saying about gauge fixing away the conformal mode was in terms of the integration over this data at late time. That data is only defined mod diff times vial on the d-1 dimensional slice at late time. So that metric, that spatial metric, you can, there's a conformal mode, but it's pure gauge.
So actual computation we perform, we are doing whatever background and small fluctuation around. It's a Gaussian computation.
Yes, that's right. Yes.
This computation holds equally to first and second order formalism.
It holds what, sorry?
First order formalism and second order formalism.
So we did it in the second order formalism. I don't expect anything to be different in first order, but I haven't done it. So I think yeah, it should, I think it's the same. I don't see a reason why it shouldn't be the same. Yeah. I mean, even in the first order formalism, I mean, you have, okay, so you introduce spin connection now, but in terms of what are the right boundary conditions that you would impose, they would still, at least in this problem where I have late Lorentzian time, I would still impose these de Sitter boundary conditions. And those are labeled by still boundary values of the metric, conformal classes of boundary metrics.
There are some complications, I think, in the first order formalism. They are not equal, at least in the partition function.
Well, the issues that arise in the first order formalism are that, you know, it's usually the ones that I'm aware of. Maybe this is what you're thinking of. Maybe you're thinking of a different issue. You know, people often, especially in 3 dimensions, like to write first order formalism in Chern-Simons variables. And then there's the question, is gravity equivalent to a Chern-Simons? And there are, you know, in the ADS context, this is now very well understood. When you have a saddle point approximations, when there's a hyperbolic metric on your 3-manifold, then the two things agree. There's only one quantization. But on the general 3-manifold, it's not the case in Chern-Simons, and gravity will disagree with each other. Is that what the sort of thing that you had in mind was the Chern-Simons? Okay. Okay. Well, let's end. Thank you.